I would like to welcome all of you to the Michigan AI Symposium. My name is Rada Mihalcea. I'm the director of the Michigan AI Lab. And on behalf of our lab, I would like to welcome you all to today's event. We have a wonderful day ahead of us, filled with great ideas that are pushing the envelope in AI, helping build systems that are positively impacting our society. We are very excited to have you all here with us today. The event is hosted by the AI Lab at Michigan, a research lab that goes back to 1988. And in the 30 and more years that passed since then, our lab grew to more than 25 faculty, 90 PhD students, several postdoctoral fellows, and many master's and undergraduate students who all work on research in the core area of AI. We work in machine learning, which includes deep learning and reinforcement learning, on computer vision, natural language processing, graph algorithms, speech processing, cognitive architectures, robotics, AI-human interaction, and more. While some may fear that AI may replace us, we here in this symposium know very well that on the contrary, AI has the ability to complement and strengthen us. And this is the very theme of today's symposium, human-AI collaboration. The symposium brings together several amazing speakers. We have two keynote addresses from Professor Julie Shah from MIT, and our own alumna, Professor Melanie Mitchell from the Santa Fe Institute. We have 6 invited talks from the Michigan AI Lab, as well as 5 lightning talks, which are accompanied by posters from rising stars in AI. We also have an exciting poster session with more than 50 posters. Toward the end of the symposium, we'll have 5 breakout rooms that will give us the opportunity to have conversations with the speakers. I would like to draw your attention to the best paper awards that we'll be giving. So a heads up that during the poster session, you'll have the opportunity to vote for your favorite poster. And the winners of the best poster awards will be announced in the closing session. I also want to take this opportunity to thank our symposium sponsor, Ford Motor Company. Now, before I hand it over to our first session chair, I would like to go over a few items so you know how to participate in today's event. We are using a combination of Zoom, including webinars and regular Zoom rooms, and the Gather Town environment. The talks are all over Zoom, in which all attendees are in listen-only mode, which means that you cannot chat, but you can ask questions through the Q&A functionality. And you can see that at the bottom of the screen. You can send questions at any time during the presentation. We're collecting them and address a number of them during the Q&A session at the end of each presentation. With that, I hope that you will enjoy the symposium, and I will hand it over to my colleague and symposium co-organizer, Professor Joyce Chai, who is going to introduce the first keynote speaker. Joyce?
Thank you, Rada. Good morning. I'm Joyce Chai. I'm a professor at the Michigan AI Lab. It is my great pleasure to introduce you Professor Julie Shah as our first keynote speaker. Julie is a professor of aeronautics and astronautics at MIT. She's also the director of Interactive Robotics Group at the MIT Computer Science and Artificial Intelligence Laboratory. She received her Bachelor of Science, master's degree, and PhD degree, all from MIT. Julie's research is at the forefront of human-robot collaboration. She develops novel computational approaches that expand human cognitive models to artificial intelligence. Her work has generated many innovative forms of human-robot teaming in domains such as manufacturing assembly lines, healthcare applications, transportation, and defense. In recognition of her significant research contributions, Julie has received many awards, such as a Radcliffe Fellowship, IEEE Career Award in Robotics and Automation, NSF Career Award, and many Best Paper Awards. Julie and I have an ongoing collaborative NSF project together. It has been a great pleasure working with her. Julie has brought in tremendous insight. My students and I have learned a lot from this collaboration. So today, we're very excited to have Julie join us and talk about human-machine partnerships and work of the future. So before I give the floor to Julie, I would like to remind the audience that If you have any questions, please free to use the QA channel at any time during the talk, and we'll keep these questions to the end. So without further ado, Julie, the floor is yours.
Thank you so much, Joyce and Rada, for that wonderful introduction. Thank you so much for having me. It's such an honor to be here and kick off this event with you. So I'll go ahead and share my screen. I'm excited to share with you some of the latest work from our lab. Yeah, I'm a professor of aeronautics and astronautics at MIT, which you can map to, I love time-critical, safety-critical applications. And I'm a PI in the Computer Science and Artificial Intelligence Laboratory, where I lead a robotics group. And my group focuses on developing AI models and algorithms that are capable of modeling people, modeling human cognitive state, human workflow to facilitate more effective collaboration between humans and machines. I've spent many years working in robotics for manufacturing, developing and deploying collaborative robots that work alongside people in factories to build planes and build cars, as well as intelligent decision support for experts like nurses and doctors and fighter pilots. And the key vision behind my lab's work is to be intentional about developing computing that augments human capability rather than replaces human capability. And now I mentioned I've worked for many years in robotics for manufacturing. This is a domain that I truly love. And it's also one in which there has traditionally been concern founded around the role of robotics and automation to supplant human work or to undermine the quality of human work. And a key aspect of my lab's research has been aiming to show how this is not inevitable, that we have control over the problem framing for the technology that we develop. And there are many ways in which we can develop technologies that add value, that can improve efficiency, productivity, but also provide humans flexibility to do their best work. So center the human and design the technology to augment and enhance human work. Now, when we look at many examples of successful deployments of robots kind of in the wild, in factories and in warehouses, even today, we do have really excellent examples of human-robot interaction, but notably, the work between the human and robot is still often sort of decomposed or separated. So in Amazon's warehouses, we have interesting examples of decomposition of work going back from the Kiva systems, in which rather than a person walking up and down the warehouse, the shelves are actually robots and they bring the product to a human picker at the edges of the warehouse. And then the person does the sort of dexterous work of removing that, boxing it to ship it out. But the work that a person and robot are doing are in physically separate spaces. Similarly, on many manufacturing lines, we have the introduction of these new robots, these human-safe robots. You can remove the cages around them. They won't, I call them mostly not dangerous robots because they can still hurt you, but they can be designed and the task can be structured in such a way that they are acceptable to put right alongside a person. But even these systems, and this is a picture from one of BMW's lines, are still doing work that's independent of people, not interdependent. And so these systems are kind of coexisting rather than collaborating. Now I want to draw a parallel for the trends in these sectors to our everyday lives. And I like interaction in talks, so I'm going to try to use the Q&A in reverse. Now I'm going to ask you a question. I'm going to anchor, and then you adjust. So I'm going to anchor you with a true fact that there are about 1.8 million industrial robots in operation around the world today. 1.8 million in operation around the entire world. How many robots would you say or guess are in U.S. homes today? So I'm going to look to the Q&A. I have it open and I can see it. So someone throw out a guess. How many? And those are things that look like robots. 800,000, 1 million. Any other guesses? 10 million, 1,000, 80,000. Okay, I love this because it doesn't matter 200,000. It doesn't matter what audience I bring this to, roboticists or like a public audience. The spread is always exactly the same. It basically ranges from like 200,000 to 50 million. So interestingly, the number of things that look like robots is 30 million robots in US homes today. which is a lot. It's a lot more than there are industrial robots in operation around the world. And those are just in homes. Those are things that are robots that look like Roombas. They don't count, sidewalk delivery robots, security guard robots, service robots in work environments like hospitals. It doesn't count the hundreds of grocery store robots, these strange googly-eyed robots that are in hundreds of grocery stores around the country, going up and down the aisles. I encountered one in one of the suburbs outside Boston. It doesn't include, Alexas, things that we don't traditionally think of as looking like robots. So we have a lot of these systems actually in our life today. But it doesn't really feel as though they are providing value to us. We don't really think of them as being in our lives on a daily basis. And I'd argue the same limitations that we see in the industrial environments for the ways that they're limited in providing value there are the ways in which these systems are limited in providing value for us in our everyday lives. And that's by and large, these systems, they don't see us as people. They're not capable, even in a factory setting, of integrating into a workflow, of working interdependently with people, of complex dependencies with people. They see us as objects. And that's, problematic for a number of reasons. And when we think about, these systems at scale, today they're largely doing narrowly specified tasks in fairly structured environments. If you think about the Roomba, essentially under constant oversight. And if we look at what it will take for these systems to provide value at a much larger scale, we can extrapolate for the problems that exist when these robots only see us as obstacles. So this is a headline from a few years ago in San Francisco. And at that time, there were actually so many startups testing sidewalk delivery robots on the sidewalks of San Francisco that there was a revolt. These systems, they're large, they're heavy, they just see people, or they did just see people as obstacles. And the elderly and people with disabilities felt unsafe on their sidewalks, maneuvering and negotiating around these systems. To an extent, that may very well be justified, those concerns. And the result was these systems were removed from the most populated areas of the city. They were relegated to an industrial sector. And there were limits placed on how many could be in operation on any city block at a time. And so this is like a canary in the coal mine, like a Roomba bumping into your ankle in your home occasionally is fine. Now imagine like dozens of the equivalent of those systems, much bigger, much larger, interacting and impeding elements of your everyday life. And those don't become small frictions anymore. Those become deal breakers for the use of these systems in the real world and at scale. And so the key sort of motivation behind my lab's work is to enable these robots to see us as more than people and to be useful in sort of complex environments where teamwork is required, where interdependency is required. So in an automotive setting, if anybody has ever been through an automotive plant, it's just an astounding, it's really an inspiring view of teamwork. If you think of, building a car, it's very high volume, is a very, very repetitive task. But when you observe at like the time and motion study level of what it requires to build a car, actually half the build process is still done entirely manually. Half the build schedule, half the factory footprint is devoted to manual work. And it's done in teams. It's almost this ballet dance of load sharing, task sharing, adjusting the timing of actions, picking up slack when someone takes a little longer to rework an item. And so what would it require to be able to observe a human team working in this way and be able to take out one of the human members, say, and put in a robot to function as effectively as one of the human team members? And I will also note that it doesn't have to be a direct replacement either. The concept of decomposing work that's being done and thinking about what can best be done by a robot and what can be done by a human. Once you put that back together, the challenge is an integration challenge. So what is necessary to be able to address this type of integration challenge? So we can draw from actually decades of study in human teams, teams of nurses and doctors, surgeons working together in an operating room, of pilots and co-pilots, and how they communicate, train, and coordinate, sports teams as well. And you could summarize sort of those many decades of research on, human team coordination and training with, this sort of pithier statement of, what does it take to be a high-performing team? To be a high-performing team member, you need to know what your partner is thinking. You need to be able to anticipate what they'll do. And then you need to be able to use that information to make fast changes in response to disruptions or as circumstances unfold. And so my lab has worked in developing those capabilities of enabling a robot to infer human mental state, to be able to anticipate what a person will do next, both in their physical motion, think about working alongside someone in a factory, and both in terms of their the steps they take in solving, in doing sort of a more cognitive task, and then being able to use that information through dynamic plan execution, enable the robot to adjust and preserve the flexibility of the person, similar to how they would work, more naturally with another person. And we focus on developing those three capabilities for purposes of sort of three sequential steps necessary to build up an effective team member. So the first step is being able to plan, what you'll do together. So think about an emergency response team sitting around a table, looking at the map, figuring out who's going to do what materials are going to be deployed at what place. The key part of that is understanding like the interdependencies between team members so that you can adapt when things inevitably don't go as planned. But of course, we don't. I won't talk about it today, but we have developed techniques for aiming to integrate intelligent agents to support and track and monitor this human team planning process. But of course, we don't aim to elaborate every possible contingency, every possible outcome or action that a person will take in advance. We start out with a plan, but it needs to be refined. We refine our plans. Think about like a game plan for a team. You refine that plan through training, through experience, and through practice. So developing the techniques that enable a robot to learn by watching human work, but also through interaction and through training together. People need to train on technology. People need to train on how to work with robots. They need to train on how to work with people as well. So techniques for refining plans, and then ultimately taking those refined plans and then playing the game and executing. And I'll focus on refine and execute today. And I'll do this by I'll motivate our current line of work by looking a few years back, a project from about 5 years ago, which we were very proud of, but as any good project sets up the next dozen research directions that you want to pursue. So this was a project with a hospital in Boston, Beth Israel, and we were aiming to be able to support the role of a resource nurse on the labor and delivery floor there. So the woman here is a resource nurse, also called a nurse manager. And essentially her job is to be the air traffic controller of the labor floor. So it's this very senior person in this role. And she's responsible for taking in all of the information about the patient status and the babies and everything that's provided across those LCD screens that you see, and taking information about the current state of the patients in the labor floor as kept up to date from that handwritten whiteboard over to the right. And she's solving a very challenging resource allocation and scheduling problem. So she is deciding which patients go to which rooms, which nurses are assigned to which patients. She controls aspects of the OR schedule and many other decisions. And when you actually work out the computational complexity of the problem that she's solving, it's more complex than the problem an air traffic controller is solving. And she does it, unlike an air traffic controller, with no decision support. And so the question here for us was, what could be enabled by being able to anticipate, the possible decisions that she would make, and then support her in that role of making those decisions. And this is made more challenging because there's no training book, there's no codified training process, there's no ground truth you can refer to on whether a decision that was made was high quality or low quality. These nurses are trained through years and often decades of apprenticeship. And it's a very challenging task that they're doing. Much like air traffic controllers talk about being born to be air traffic controllers. There's very, very few people in our world that can be air traffic controllers. These nurses speak about this the same way. Some people can just cut it. Some people can't do this. It's a select group of nurses that are able cognitively to take on this very, very challenging sort of mental computation task. And it's very important to the hospital. So small decisions that this nurse makes, the margin of a hospital is very, very slim. And so small decisions on resource allocations that this nurse makes can put the hospitals in the black or in the red financially, which is also very interesting. So we worked on developing a machine learning model that could observe the decisions that these nurses were making and aim to codify that in the form of a policy. So what are the underlying rules and heuristics that a nurse is using? And we were sort of very proud of this technique. You think of it learning from demonstration for task assignment and scheduling problems. And I could give a full-length talk on how that technique works, but for purposes of this talk, it's important to know, this great result, nurses and doctors agreed with the ultimate systems recommendations 90% of the time. But what did it take to produce that result? It took embedding, an outstanding machine learning PhD on the labor and delivery floor for the better part of a year to help make explicit all the implicit factors that this nurse was taking into in account of their decision making, to be able to use those as features in the machine learning model to then learn the policies and heuristics, based on those features and the full set of information the nurse was utilizing in their decision making. And that is not a scalable process. So, we don't have enough machine learning PhDs. And it's also notable that, even after the entire year spent in the great success of this project, we still found surprises. So I'll tell you about the surprise. I'll quickly show you the video of the system in action, and then I'll tell you sort of one of the surprising features that we didn't anticipate.
Right, like, and it kind of made me like. I recommend placing a schedule so that the attention patient remarks on nurse Meredith can take care of her.
Okay, so that's the full set of information that the nurse takes as input. We evaluated the system in computer-based decision support and embodied decision support.
I recommend placing a new patient in triage bed number 5.
What is a bad decision?
A bad decision would be to place a scheduled cesarean section patient in group 14 and have Nurse Kristen take care of her.
Ginger, what's a good decision?
I recommend placing a scheduled infection patient in group 10. Nurse Meredith will take care of her.
I don't know if you plan to go back and watch it. For me, it was like this one.
Ginger, what's a bad decision?
A bad decision would be to place a scheduled cesarean section patient in group 8 and have Nurse Amy take care of her.
I agree.
So this gives you a sense of what the system is doing when it's recommending decisions. The concept of the system was to be able to make suggestions or recommendations so the more straightforward set of decisions to be made to free up the nurse's cognitive capacity for the other more challenging decisions that they need to make on a daily basis. Despite this very intensive process, in the end, when we were inspecting and validating the learned models with nurses and doctors, we uncovered something interesting, which was that there were other factors that appeared to affect the nurse's decision-making. For example, there appeared to be an effect of busyness of the labor floor. And it turns out in investigating that further, no nurse raised that. When the labor floor is busy, I make different decisions. But in fact, C-section rate increased when the labor floor was busy. And then once you dig into that, there are actually, good reasons that might exist. In particular, when you're making very difficult decisions under ambiguity and uncertainty, a labor can take any amount of time. You have limited resources available. A C-section is a very discrete, time-limited procedure to be able to plan for. And so, making a decision to do more C-sections can have many adverse outcomes, but it is, a rational strategy for reducing uncertainty and deploying the resources that you have, but undesirable for many other reasons. So, this underscores the point that we'll never be able to, fully capture the full set of features that a person uses in their decision making. There will always be these latent decision factors. And this motivated a next line of research to be able to recognize this. Much like when we're driving a car, there are like clearly known features and decision factors that we take into consideration. But from city to city, there's going to be other features or factors. And we want to be able to learn these, start with what we know and then be able to learn these, for example, with non-parametric Bayesian techniques. And so we developed a line of research in order to be able to do this, designing an agent Markov model, a particular structured model to support efficient inference, in which we're aiming to infer not just the latent decision factors, but their dynamics as well. This is a very challenging inference problem, you would desire to do it in an unsupervised way, in an ideal world, right? One of the challenges is that we aren't able to learn, to the extent that you want to learn a model of those latent decision factors and their dynamics that is aligned with a human mental model. You're not able to do that with a fully unsupervised approach. So I'm going to give you a sort of a concrete example here. Say we want to be able to learn the latent model of the behavior of a subway. I'm originally from New Jersey. So in New York, the subways go uptown and downtown. You go to the end of the line, it turns around, it comes back. But the mental model I hold of it is uptown, downtown. In Boston, you may or may not know, the subway behaves similarly from observations. It goes to the end of the line, it turns around, it comes back. But the mental model we hold of the subway is different in Boston. We say it's going inbound as long as it's going to some central, stop in the center at Park Street, it's going inbound. And then as soon as it crosses through Park Street, it's going outbound. It doesn't matter what direction it's going. As long as it's going to Park Street, it's inbound. Once it crosses, it's going outbound. So this is a two-state model switching, but my model of it in Boston is different than someone in New York. And it can be very important to align that model to a human mental model for a number of reasons, for validation, for inspection, for communication. It can also, in a more complex context, aligning to a human mental model can support the predictive power of the model or the person's ability to predict the performance of the machine learning model when it's making predictions. In many cases, it's very difficult to collect labeled data. And so we became interested in how we could learn these latent factors and their dynamics with relatively little input from a person and from someone who is not a machine learning expert. There are many forms of input a person can give, and in fact gives others to help teach or train them, other than these labels, these lower level labels. And so what we did was take these various forms of input and formulate them in the form of partial policies, partial dynamics, as constraints on a variational inference process that can shape that latent space and improve the efficiency of the inference process. So, for example, if I may not be able to tell you in New York or Boston, the particular label or name of, the subway state, but I can often tell you as a non-machine learning expert when in my mind the system switches state. So I could tell you there's a change point as it moves through Park Street, or there's a change point at the end of the line. And that's actually enough to be able to guide the inference process to learn a model that aligns with the human mental model in many cases. So this process of taking those types of sort of high-level input from a person and making use of them in the inference process, we formulate them as constraints on a variational inference process. And the technique we developed is called constrained variational inference, where the goal is to take much less information, easier to provide information from a person, improve the efficiency of the inference process, and again, align it to a human's mental model. So we demonstrated this in the context of a few tasks in human-robot collaborative tasks in that sort of simple subway domain I mentioned, and in other domains where, for example, a car is overtaking another car in a lane. And we have, in the human-robot context, we have known decision factors like the position of a person in space. If we're tracking their hand with motion capture, we know where their hand is. We have latent decision factors, which can represent many different things. For example, the person's own held priorities or preferences for executing a task, or the sequences in which they're going to do their work. It can represent other factors that impact humans' behavior, for example, workload or fatigue. In the context of the human-robot collaborative task I'll show, we define motion primitives as at the motion planning level. So, the person's sort of motion through space to reach out and manipulate a next object as a part of their task. And the latent parameters that we're aiming to learn are the latent decision factors, the initial, probability distribution over them, and the transition function over them. So it's a challenging inference problem. And what we're able to show in using constrained variational inference is, first of all, that this is both in synthetic and in human-robot experiments. With a fully unsupervised approach, as expected, the model is not able to align to a human-held mental model or a ground truth model. With a fully supervised approach, we are, but that is very intensive in terms of label and input from a person. With this hybrid approach, taking these few pieces of high-level information, we're actually able to achieve comparable performance to a fully supervised approach, which is really exciting. And so this is a little bit about, how we aim to learn, give the robot a model of the human's behavior to be able to predict, to infer human mental state and predict what a person will do. The next thing we need to develop this robot into an effective team member is to give it a model of the task. We could do that directly, but we're also equally interested in allowing people who are not robot experts the ability to give the robot a task model and to refine it, so that the robot can together use that human model, maintaining a belief over the human's priorities and preferences or goals, and a task model as well, potentially maintaining a belief over how to execute the task successfully. And be able to reason on that uncertainty to make informed decisions on action and communication. So a little bit about teaching a robot a task model. So we have many techniques to do this that are very powerful, for example, inverse reinforcement learning. But in some cases, they're useful but not sufficient. So, in some cases, it really, especially in time-critical, safety-critical applications, learning a reward function is valuable, but it's equally important to be able to learn the delineation between acceptable and unacceptable performance of a task, which can be a very clear, bright line. And so being able to infer or learn these task specifications is useful in a few contexts. One is that depending on the form of the task specification, it can be more interpretable to a person to inspect and validate. And then, there's many techniques we can use in learning a task specification in order to, synthesize verifiable controllers that can actually be directly used as a reward signal during reinforcement learning. It can be valuable for a system model for execution monitoring. And so we aimed to be able to develop a probabilistic model for inferring the temporal structure of a task in the form of a linear temporal logic specification. And people can do this with really few demonstrations, which is interesting. So I'm showing you this, think of it as a ground vehicle here, maneuvering through a few sites of interest, which are the green circles, and maneuvering around these red circles. And just with these 4 examples, if I were to say, how would you specify successful performance of this task? And people typically say, okay, I see the ground vehicle needs to move through points of interest 1, 2, 3, 4 in that specific order, unless that point of interest is in this kind of red no-go region. And that's it. We can do that with 4 examples. But a machine cannot or could not, do that with just 4 examples. So why are we, why are we so good at this? Why is it so computationally hard? One of the things we really like about linear temporal logic is the flexibility it affords us for specifying behaviors. But that is also its key challenge. Like inference in this very large hypothesis space is very challenging. Now, how do people do this? Like, how did we just do that on that previous example? It turns out that people, this is documented in the cognitive science literature, actually, when we're building complex systems like software systems, or we're trying to build our own mental model of how a complex system functions, people commonly use a subset of temporal behaviors in building their understanding of the behavior or in designing programs. And so what we do is we draw from those templates. Dwyer et al. Has like 20, 25 or so kind of templated behaviors. We draw from a smaller number of them. And we define prior and likelihood distributions over a smaller but relevant part of the LTL formulas using these templates from Dwyer et al. And so the ones that we draw from are including sort of global satisfaction of propositions, which would allow us to say something like always stay outside a threat avoidance zone of a subset of threats. Sort of conditional statements that allow us to specify kind of like completion of subtasks, eventually visit a subset of accessible points of interest. And then we have ordering constraints of various complexity that we can introduce. And we look at a few different variations of ways of specifying sequencing. But for example, in terms of sequencing, you'd want to specify, visit a subset of the points of interest in some specific order. So we aim to infer an LTL specification as a conjunction of these three templates: global, eventual, and order. And by defining, prior over, like, this space and a likelihood function that is also inspired by cognitive science, but is designed to be domain independent, we find we're able to achieve a good performance in inferring LTL specifications. So in this very simple synthetic task, we're able to infer the correct LTL specification with, on the order of about 10 demonstrations. So not 4, but 10 is pretty good and significantly outperforms the prior art. And we use this in other more complex settings as well. So we had a number of people come in and provide demonstrations for setting of a dinner table according to various menus and aim to extract the LTL specification from that. Just via those demonstrations, we can extract it quite well with on the order of 70 demonstrations, which is exciting. And we also were able to employ this technique for inferring LTL specifications for mission level objectives of large scale Air Force air exercises. And so, it's scalable in terms of complexity, number of agents executing. One of the key benefits of employing a Bayesian approach for trying to infer a specification, like an LTL specification, is that we don't just extract one specification. What we get from this process is actually a belief over specifications. And we can leverage that in interesting ways. So first of all, even with one LTL specification, compiling a policy for that specification affords us a lot of flexibility. There are many, many different ways to satisfy that specification, and many different sort of rollouts. So I'm showing you here the robot after it's learned from those 70 demonstrations on how to set a dinner table. It's proceeding and setting the dinner table with many different possible orders, and all are equally valid. One of the things that's really exciting about employing LTL in this way is that if you think of the person as an uncontrollable entity, they might move objects on the table. They might occlude for some time an object that the robot needs. Here we're hiding the plate all the way to the right, and the robot will just proceed in executing the task with one of the rollouts that meets the spec, and leave that plate till the end, kind of without throwing an error. And eventually, when that plate is unveiled, the robot takes it and finishes out the setting of the dinner table. This is a technique not just planning with a single LTL specification, but planning with uncertain specifications or puns. And planning with uncertain specifications provides you an interesting design space. So if you have a distribution over possible specifications, you can begin thinking about how you hedge against that uncertainty. In some contexts, you want to be very, very conservative, very, very risk averse, and only choose the rollouts that are going to meet, just about all of the possible specifications that might be the true underlying specification. In others, you may allow for a little more creativity. And so there are different ways in which you can compute policies based on this belief. One of the other really exciting aspects of maintaining a belief over specifications is that it allows a way for the robot and person to sort of directly interact through an active learning process to reduce the robot's uncertainty about what the person is trying to teach it. And this can have big implications for manufacturing context, many others as well. But speaking a little bit about manufacturing, we want to deploy collaborative robots, but we also, there are many reasons why we just want to deploy more robots. There's this, the sense from many that robots are supplanting work and that this is a threat. Actually, small and medium firms across the US are lagging in their adoption of new technologies, including robotics. And there's a long sort of scholarship and history of linking the technological upgrading of small and medium firms to the competitiveness, to the economic competitiveness of our manufacturing base in the country and issues related to national security as well. We actually want more of these small and medium firms to use more robots. They often can't because of the resources required to program the robot. There's an automation engineer that sort of sits between. And a big firm can hire an automation engineer, and every single time the task needs to change a little bit, that automation engineer can come in and do that. But a small firm with 100 employees less, or even just less than 500, often doesn't have the resources, and it's very expensive to go outside for those resources. And so I was fortunate to be a part of the Work of the Future task force at MIT, which ran from 2018 and just finished up, in which my team, along with a number of social scientists, visited many manufacturers, integrators, OEMs across Europe, looking at how they were using advanced technologies, barriers for the use of those technologies, and another team that looked specifically in the US at small and medium manufacturers. And these integration costs were paramount. And the other interesting thing was, how these companies thought about making the business case for the introduction of the robots. The labor displacement, directly introducing a robot to displace labor, was viewed as outdated, and that much of the benefit was in this augmenting or assisting role. But it's ironic, right? Because deeper integration of the human-robot work was the goal in many of their minds. But it's hindered by integration challenges. And even worse, how you make the business case for integrating a robot, is it going to prove in all these various ways, actually requires simulation. Actually, it requires even more technical expertise rather than a simple labor displacement calculation, which is very standard. This integration, this ability to be able to leverage shop floor domain expertise to explore and figure out how to utilize these robots without someone who is a robotics expert was sort of paramount and highlighted over and over again. So the need to program the robot, not the need to program the task, not the robot, was a key takeaway. And so in aiming to learn a task specification from demonstrations are valuable because you don't necessarily need to be a robot expert. You can just sort of show how to set the dinner table or show how to do the assembly task. But 70 is a lot. 70 demonstrations is a lot. It's a way more than a person needs. And so, what can be done to reduce this number very substantially? We can leverage the fact that in using these techniques, the robot is maintaining a belief over the ground truth specification for how to perform this task. And this provides a rich new set of options in which that robot can actively solicit the information that it needs to be able to refine its understanding of that boundary between successful and unsuccessful execution of a task. And of course, the benefit to it maintaining a specification is that it affords a lot of flexibility in this more dynamic environment when it's integrated. And so in this case, we looked at a paradigm in which the robot took a few demonstrations from a person and then would demonstrate back something very close to that boundary of acceptable versus unacceptable in order to maximally reduce its uncertainty over that boundary. Or it would just openly solicit, another example from the person. And so I'll give you we ran these experiments in COVID time. So these were all people from their dorm room or otherwise interfacing with the robot through, a remote interface, not physically demonstrating. But that's exciting too. Imagine a remote person teaching a robot in a shop, how to do the task that it needs to do for the day. So the person would essentially, coach step by step the robot through the task the way they wanted it done, essentially teleoperating the robot. They would take, 2 demonstrations in this case. The person would kind of set the dinner table twice. Now the robot is uncertain. So what it's going to do is try to set the dinner table and then ask, was that acceptable or not? And you can see here, this is not acceptable. The plate was placed on top of the bowl. So the person would say, no, that was not acceptable. The robot would set again. And the robot would say, is that acceptable or is that unacceptable? And via a little app, the person would click, oh, yes, remotely, that one looks acceptable. And then, we do this query, and sometimes the robot would select for the person to just give a whole new demonstration. We looked at the relative benefits and when you would, choose one or the other. And so through those 5 interactions, again, not 70 now, through those 5 interactions, the robot learned a very high quality model of how to perform that task, which is quite exciting. Now what we're currently working on is moving this into a multimodal setting. You can imagine maybe the person doesn't have to physically do the task, or maybe does a part of the task and describes how elements of that task are repeated. And also this can be done in simulation where, there can be high cost to a robot really doing a task wrong in a physical environment, but a robot showing in a virtual environment and providing that as sort of a training ground to fix up the task specification can be very valuable as well. Okay, so this is a little bit about our work in taking more natural inputs and very fewer inputs from a person to be able to learn a human model and to be able to learn a task model. And then what we aim to do is put it together. So this is recent work from our lab. This is the PhD work of Vebaf Unhilker. And what he did was take the task and human model and formulate that together within a POMDP, within a fairly large action space, like 2 times 10 to the 6th, and be able to enable a robot to plan, in this case, just based on uncertainty in the human model, not the task model, but just the human model, plan at a horizon of 0.3 seconds, the actions it will take, and in some cases, the communications it'll take. We looked at handover tasks, and then we also looked at interdependent collaborative tasks in which the person and robot are both doing work in a shared space. In this case, the person is preparing sandwiches at 4 stations. The robot needs to pour juice, and the robot needs to share space safely and efficiently with the human, anticipate where the human will be, stay out of that region. The robot within this POMDP is doing its motion planning, not just choosing what location to go to next, but actively planning its trajectory through the space. So hence the large size of that POMDP. So it's choosing its actions sort of at the motion level. And when we also incorporate communicative actions. So in some of these studies. So the robot, we know again from those studies in human-human teamwork, that explicitly commanding a partner is among the most inefficient ways of coordinating the work of 2 people or multiple people working together. A more effective low overhead way is to offer information or resources at the right time. So provide status updates. Pilots do this with co-pilots. Instead of telling the other what to do in sequence, they'll offer information very regularly about what they are doing and about what they will do next so that the other can incorporate it into their own action planning. So in this context, if the robot is very uncertain what a person will do, it might explicitly command the person to avoid an adverse outcome, but otherwise it will proactively choose to communicate its status updates. And it's using that POMDP to selectively communicate status updates when they're most valuable. Again, that human model was learned through constrained variational inference, and we see a higher quality model learned through constrained variational inference than if you tried to handcraft a model for the robot to work with the person, and about comparable or improved upon if we used a fully supervised approach to learning that human model. And we also see a benefit to communicating. And so you can see here with a handcrafted communication model, the robot communicates actually a little less than with our POMDP model, but to good effect because the human robot team is performing better with communication. So, so there's some intelligence to communicating slightly more than with an intuitive handcrafted model. The human robot team sees benefit in their team performance. So I'm going to finish up by showing you this video of the person and robot working together to make those sandwiches. The person is doing the dexterous work of preparing the sandwiches. The robot is pouring juice, which is not juice because liquid is not good for robots. So it's like marbles. And they need to deconflict their use of those 4 stations as they're working through this task. The robot is maintaining a belief based on the model learned through constrained variational inference on the person's priorities and preferences where they're going to work next.
Let's make some meals. I will pour juice. Please make and wrap the sandwiches. Let's start.
So the robot can choose to communicate about every 0.3 seconds.
Please make the next sandwich at 2.
So at the start, the robot was very uncertain what this person would do, and so did explicitly communicate a suggestion for where to go next. Once the person is there, the robot doesn't repeat the communication. Okay, so in that case, you could see the robot did not communicate. Actually, it's choosing not to communicate every 0.3 seconds because it has a strong belief over where the person will be next. And it moves in to pour the juice at 2.
I am pouring juice at 3.
In that case, the robot offered that status update. I am pouring juice at 3, just to make sure the person knew they could, plan on their own to deconflict.
I am pouring juice at 4. I am pouring juice at 4.
And in that case, the robot repeated the communication because after that first communication, the robot didn't have enough information based on observing the human's hand about where they were going to, and the uncertainty wasn't reduced sufficiently based on the following observations.
I finished pouring juice,
and that's it. So this is really exciting. This is bringing together multiple PhDs over many years to begin, integrating these into capabilities that allow a robot to easily, through relatively little interaction, learn a human's model of how they'll perform the task, learn the task as well. That's not integrated into this demo. And then be able to use that rather than sort of waiting to be explicitly commanded, use that richer model of the human rather than just as an obstacle, inferring aspects of their latent state and the dynamics, to be able to be a more proactive collaborator to the benefit, as we show in our experiments, the empirical benefit of the team's performance. Okay, and so I know I'll wrap up in just a moment. I think I want to just talk about one more thing, which is that I also come to you today with a role as Associate Dean of Social and Ethical Responsibilities of Computing within MIT's new Schwarzman College of Computing. So my co-associate dean, Dave Kaiser, and I from Science, Technology, and Society, we're building up this cross-cutting area of the college where our aim is to impact research, how research is done at MIT, our teaching, as well as also help facilitate, broader engagements with the vision of actively incorporating social, ethical, and policy considerations into the research, teaching, and implementation of computing. And as a part of this, I've had this amazing pleasure of working with over 70 faculty over the last 2 years across MIT to develop new course content, build new course material, develop resources, thinking about responsible research practices at MIT, and changes we can make there. Is a part of our goal of bringing our students, our ECS students, a broader perspective of the scale and impact of the technologies that they develop and the impact of even small design decisions, at a much larger scale. We've launched the MIT case study series in social and ethical responsibilities of computing, in which we solicit and commission from scholars, world-renowned scholars from across disciplines, not their whole book, but like 3,000 to 4,000 word cases, we call them. So they take 10 or 15 minutes to read on a variety of topics: privacy, surveillance, data collection, who collects data, to what end, looks at particular technologies like facial recognition, use of AI in the criminal justice system, looking at it from an engineering perspective about how to parse sources of harm throughout the machine learning lifecycle, robotics as well, in national security. We have a case on that recently came out, and many more in the works. And so I want to point you to this because they are really, really fun reads. They're meant to be kind of inserted into a number of different classes without, crowding out any other content. And without having to read, a full-length book. They're designed for those that don't have prior, expertise or in a particular field. And so you can find these cases at MIT-CERC, which is Social and Ethical Responsibilities of Computing.pubpub.org, freely, openly accessible, materials. And so with that, I will stop, and I'm delighted to take any questions. Thank you so much.
Great. Thank you, Julie, for the wonderful talk. And we have a few minutes for the questions, and see that there's quite a few questions on the channel. So seems like quite a few people are really interested in this nursing robot. One of the questions is really about what kind of features that do you use the structured and unstructured data to train these robot. And there's another question related to that is, why do you choose to use now? And then another question. So I'm just trying to summarize these questions. One question is also about like when the robot making the recommendation to the nurse, like to the doctor, like nurse A shouldn't do this, nurse B shouldn't do that. Okay, what is could be the implication to those nurses? Would the robot actually explain why such recommendation is made, right? Is the nurse A is just incompetent, or nurse A is busy, or so maybe you can give some the comment on these questions.
Yeah. Okay, I could talk way too long about that. That's the PhD work of Matthew Gambale, who's an assistant professor at Georgia Tech, and he continues the line of research on those methods as well. So in order to learn from demonstrations to learn policies for like task assignment and scheduling problems, the sort of trick there is to not just sort of take a trajectory of the demonstration, but recognize that when people are learning in sort of multi-criteria decision-making problems, we do more than just to observe the decisions that are made. We do this like mental differencing. So every time a nurse makes a decision, the apprentice, like the medical student following them, shadowing them on the labor floor, is thinking like, okay, they made this decision, but they didn't make these 7 other decisions at this point. And humans are always computing these pairwise comparisons from every single data point we get. So what the machine learning model there does is assume that structure. It computes these pairwise comparisons within the decision space and the feature space. So it's a way of bootstrapping the learning with this assumption underlying it. But once you do that, you can actually use that in any machine learning model. So we looked at SVMs, neural nets, decision trees, random forests. So with relatively little data, maybe it's not surprising, but decision trees outperformed the other methods and random forests as well. But part of that appears to be because human decision making is modal, which is captured well by those decision trees. But what that provided us was an opportunity to sit down and work through those decision trees with nurses and doctors to validate them, to really understand what was learned in that decision tree. It's a more interpretable model, but still very, very hard to work through with a domain expert and understand, like, does this map to their own decision making? So that was fortunate. In the first iteration of that project, we developed a high fidelity simulation environment that reproduced all of the streams of all the feeds that the nurses were taking. It emulated the process of labor for different patients with different conditions through probabilities that were refined for that particular hospital based on their real data. It was a very intensive process to set up that simulation environment. And in the first round of collection of data, we used real nurse names. And then when we inspected what was learned, it turned out that we were learning particular personal preferences of particular nurses. There's a particular nurse who takes a break at a certain time. There's a particular nurse who only takes care of these types of patients. Those types of those aspects are actually really, really important to making a decision support system work in a real environment. It needs to be able to learn and use those types of preferences. Otherwise, it's just going to be disused. Like once it puts someone who takes a break at a certain time on shift, obviously it's going to be rejected. But our goal here was not to learn the particular nuances of that labor floor, but to try to gain a deeper understanding of the rules and heuristics that a nurse uses for the resource problem, not tied to these personal characteristics. There were also obviously sensitivity and privacy concerns of the nurses when their sort of personal preferences of how they like to work were kind of being elevated in this way. So we conducted the data collection again, where we used names of nurses that did not exist on that labor floor. And then we were able to learn something a little more fundamental about the strategies that these nurses were using that could be used in a training paradigm. So brought back into that simulation environment, take novice nurses through, and now train them up with recommended decisions. So it's a way of scaling that trainee process for these nurses, rather than a more junior nurse shadowing the senior nurse in this one-to-one paradigm, which is very challenging, using this kind of high fidelity simulation environment. And by codifying the expert's knowledge, we can allow other trainees to train up to proficiency off the labor floor, which was one of the motivations of the project. And it was very exciting to see that use. The now robots, we're roboticists, and we wanted to know, could a robot with a camera actually read the labor and delivery floor whiteboard and actually pull out the current status of the whiteboard and actually make a reasonable recommendation based on it? Can this work? In many hospitals, that information is not in a computer system. So and now would never be deployed on this robot or on this, in this setting. But another use of this technology is in priming the tasking of service robots on a labor floor. So we have studies from EHRI field about how service robots are very difficult to integrate into these environments. And if you think about why, that resource nurse is already tasking a dozen very autonomous nurses trained up. And now you're going to give them a fleet of robots whose schedules need to be adjusted, who need to be tasked based on the very dynamic status of the labor floor. So a service robot that can make suggestions about turning over rooms and next place to go. It's much easier to confirm a decision or to check, a solution to a scheduling problem than it is to compute it yourself. And so it's a way of easing the introduction of a service robot on the labor floor. That's one of the other potential uses of that technology.
Great, thank you, Julie. We're running out of time. We still have quite a few questions in the channel, and we're gonna table it. And Julie's gonna come back this afternoon in our Birds of a Feather session starting 3:30. So I would like to invite you to come back to meet Julie and continue the discussion. So thank you, Julie, and thank you, audience, for a wonderful session. Next, I'm going to turn over to my colleague, Emily Moore Provost, who is going to chair the next session on human AI collaboration.